I will begin. As you guys know, I have been sort of stuck in chapter 4, right? And I'm going to go on. I really, the part of 4 I haven't done justice yet to. We'll come back to that stuff later, and I'll try to attack it again there when we get to it. There are just a couple things I should mention, just for the sake of terminology, that are at the end of chapter 4. And so in section 4.7, he talks about topological properties of surfaces. So just to share with you a couple of definitions from there. The one is a surface is connected, provided that for any 2 points P and Q of M, there's a curved segment from P to Q, right? So this is connected. So I'll just write a few things here. I'll try not to prove anything, although there are some proofs in this section. All right, so first of all, here's M. It's connected if you can take a point P and you can take a point Q, and there's some curve segment alpha which starts at P and ends at Q, right? That's how he defines connected. Now, alpha is a curve on M. Right. Now, full disclosure, he says that's connected, but I think in mathematics we actually would call this path connected. This is actually the definition of path connected. And path connectedness of a topological space means what it sounds like. If a set is path connected, if between any 2 points in the set you can connect the points with a path that doesn't go outside the set, right? So, for example, Rn is path connected. So here's proof. Let P and Q be in Rn, then alpha of T equal to P plus T times Q minus P is a curve segment. In fact, it's a line which connects P to Q. P and Q being arbitrary, we're done. We've just proved Rn is connected, well, path connected. Technically connected in mathematics, I don't know if this is in his section or not, but I'll mention it to you guys since you might be interested. But connected, that means that there does not exist U and V open. So let's say X is connected. If there's not U and V open in X such that U intersect V is empty, and U union V equals to X. A pair of open sets, for which the union of the sets is the whole space and yet their intersection is disjoint, this is called a separation of a space. So another way of stating this definition of connected is that a topological space is connected if it doesn't have a separation. Now, connectedness of sets is an important property that's used throughout basic analysis courses to prove interesting theorems. If you have a course in complex analysis, there's some very critical theorems in the complex analysis course which rely on a connectedness argument. So it's more than just being a kind of abstract topological oddity, this idea of connected. Connectedness is one of the fundamental basic concepts of topology that you want to understand when you take topology. All right? Path connected is even better because it's a geometric idea, right? Now, path connected implies connected, right? So it is always the case that a path connected space is connected, but the converse direction doesn't have to be true. There are connected spaces which are not path connected. I'll let you take a course in topology to see the example of that. It's not something called the topologist sine curve, but anyway. So that's the first thing, connected. So, for example, maybe it's useful to have an example which is not connected. If you look at, for example, GL and R, so this is A in Rn by n, such that the determinant of A is not equal to 0. If you look at that set as a manifold, this is an n squared dimensional manifold, and it's in fact not connected. The reason being, you can have matrices which have positive determinant, and you can have matrices which have negative determinant, right? Those are the two cases. And so basically this is GL plus unioned with GL minus. And actually those form a separation. Those form a separation of the set of all invertible matrices. Because you can prove when you get into the details here that those are both open sets with respect to what we mean by open here, which I don't want to define because it's kind of beyond our current course. I'm just giving you we're doing some sightseeing here for a moment. But, so this is not connected because it's got two pieces which are disconnected and both open. Okay. So that's one thing he mentions in chapter 4. And then he also talks about MCompact. So what does it mean for a set to be compact? So he says a general definition of compactness is expressed in terms of open coverings. So, right, I mean, so MCompact would mean that every open covering of M contains a finite subcover, which is kind of a bit to digest. An open covering of a space, what that means is a collection of open sets whose union covers the whole space. That's kind of it. So finite means that every open covering you can pick just a few of them, and you can get enough to cover the whole space. Like it's a finiteness condition. To kind of give you a silly example, the sphere is compact. If we look at the atlas that we constructed on the sphere, that gives you an open covering, right? And if you were to take that and throw in tons and tons and tons more patches, right? You could always look at, well, there are those 6 that cover the whole thing. It's not quite the right way to say it, but anyway, kind of getting more to the point since this is not a topology course. Well, he says, lemma 7.2, a surface M is compact if and only if it can be covered by the images of a finite number of 2 segments. So what's a 2 segment for O'Neill? let me tell you what a 2-segment is. A 2-segment, so you take a patch, all right? Or anyway, take a map and take a rectangle and go up to the surface. This is rectangle. So the kind of idea here, maybe your parameter space, I don't know what the exact domain of the V and the U looks like. Maybe it looks like some kind of funky, looks like a palette from an artist or something, I don't know, whatever. And then, you know, here's your surface. Maybe it's got some holes in it, I don't know, it's a surface. A 2-segment on the surface is just like you take a rectangle in here, like so, and the image of that rectangle, bloop, bloop, bloop. There you go, that's a 2-segment on the surface, okay? Now he describes 2 segments more completely in the previous section, in section 4.6, where he talks about how we can integrate differential forms on a surface, right? And again, we're going to come back to that when we actually do some of those calculations, all right? But in short, here's a little bit more to say. It's not, he doesn't insist that the 2-segment has he doesn't insist on, I don't think, on regularity. He drops one of the conditions for the 2-segment map. But like, it's not quite as strong as a patch. But anyway, lemma 7.2 says M is compact if M can be covered by a finite number of these rectangles. Well, the images of rectangles, they're curved rectangles, right? So this makes M compact. So M is compact if and only if it can be covered by the images of a finite number of 2 segments on M. Proof is there. It's about a page long. And then lemma 7.3, he says, a continuous function on a compact region in a surface M takes a maximum at some point of M. So if this is M, all right, and you could take some subset of M like this, all right, and if that was a compact subset, right, and you take that subset and then you take another function f to the reals, right, a real valued function from the surface, a compact subset of the surface to the reals, then the theorem is that if f is continuous, it attains a minimum and a maximum. So it says basically the image of f has to look like this. Min, max, and also it has to cover everything between those, I think. So this is, he doesn't say that it has to attain everything in between, but I think that's actually true. I might be wrong about that, but anyway, this is the extreme value theorem. So in Calculus 1, we state the extreme value theorem that a continuous function on a closed interval attains a minimum and a maximum, right? That's the extreme value theorem. That theorem generalizes in the more abstract context to a continuous function on a compact set attains a maximum and minimum. So compactness is sort of the generalization of the idea of closed interval in some sense. It's a finiteness condition. Finally, he defines orientable. A surface is orientable if there exists a differentiable 2 form that's non-zero at every point of M. M is orientable if there exists mu, a 2 form, everywhere non-zero on M. And without me getting dragged too far into the details here, let me just kind of get to the point. Proposition 7.5 tells us a surface M is orientable if and only if there exists a unit normal vector field on M and furthermore, if M is connected as well as orientable, there are exactly 2 unit normals on M. All right. And actually, I think the proof of this is not, part of it's pretty easy to understand, and maybe worth our time. I'll take a stab at it. Here. So I'm not going to do the if and only if. I'm going to do like just the forward implication, all right? A little bit of it. So suppose M is orientable. Well, maybe I'm going to do both. Let me see here. I guess I'm doing this direction. Sorry, I'm thinking through it here. So suppose that there exists a unit normal vector field on M for a second, right? And let's let U be unit normal. Unit normal vector field, right? So that means that U of P is an element of the tangent space to P at M perp, right? For all P and M. And what else? The length of U of P is what? Is 1, right? So it says unit normal refers to the length of the vector field. So the definition that we've given is that it's orientable if there's a 2 form, which is everywhere non-zero on M, right? So the question is, how can I use the unit normal to define a everywhere non-zero 2 form, all right? And I can show you that without eating too much of our time. So the question is, how do we define mu? So a 2 form, all right, we have to define how it acts on a pair of vectors. So 2 forms take in a pair of vectors and they give you back out a number. So we'll take mu of, let's say, v comma w. And what should it be? How about this? U dotted with v cross w. This formula, all right, first of all, why? So here I'm saying that v and w, I mean, I can make it at the point P. At the point P, we take u of P dotted with VW, and this is for all v and w in the tangent space to P at M. So can you tell me why that's? Well, a couple of easy things. It's linear in V, right? It's linear in W because the cross product is linear in those slots, right? and the dot product is linear. So we have linearity in V and W from the properties of the dot product and the cross product. And it's also antisymmetric, right? Like if I switch the order of V and W, I get mu of WV is minus mu of VW because the cross product is antisymmetric, right? So we have bilinear, we have antisymmetric. And so it's definitely a two form, right? Now, how do we know it's non-zero? If this was equal to 0, what would that tell you? So suppose that U of P, they're not independent. What are not independent?
Or no, if it's 0, that means they're the same.
Yeah, that means.
That means like there's no orthogonality.
I would say that means that V cross W has to be perpendicular to U, right? So this would say that V and W, right, are perpendicular to U. But U of P, remember, is an element of the perp to M, right? Think about it, though. How can V and W be? How can V cross W, rather? I should say V cross W. How can V cross W be perpendicular to U of P? Remember, V and W are both in the tangent space, right? U is orthogonal to the cross product, right? That's what that means. But remember, V and W are in the tangent space, right? V cross W has to be in the normal space. And yet it's perpendicular. So the only way this can happen is if V cross W is itself 0. In other words, this forces V and W both to be 0 in order to get 0. Which is to prove that the only thing that gives you back 0 is when you have both 0, right? Which implicitly also means then that otherwise, for V and W non-zero, this is non-zero, which goes to show you that it's everywhere non-zero. So that gives us a non-vanishing two form everywhere, which is to say that M is orientable. Anyway, a more careful and verbose proof of this assertion in both directions, right, is given on page 186 to 187, all right? And as he mentions, non-orientable surfaces do exist in R3. And what's the most famous example of that? You were just telling me about it earlier, Audric. See if I can conjure one up here. Right. Take like this, and then we take like this, twist, and connect. And that is a surface which is a Mobius strip, yeah. And this is not orientable. You can't find a everywhere non-vanishing normal vector field to this if you try to do it. So what happens is if you try to do it like this, right? So you say, oh, this side of the surface is up, right? And then you start tracking around, well, let me make a mark on my starting point. Oh, I don't have a marker. But anyway, if you could imagine starting point, and you kind of track it around, you'll get back to where you started, but on the other side. But that means that at that one point on the Mobius surface, you're saying this is up and that's up. But you can't do that, right? So you can only give a normal to the Mobius strip that's like local, and then you got to but there's no way to put them all together in such a way that you get one, like, the thing is there's just one side to the Mobius strip is the thing. It's not that you can't say things about it. You can say plenty of things, but the things you can say about a Mobius strip aren't quite the same things you can say about an orientable surface. They're kind of different objects. All right. And then finally he talks a little bit about closed curves being homotopic to a constant, and then what it means for a surface to be simply connected. So I'll just say this: a surface is simply connected means that you can shrink loops to a point without getting like stuck on a hole. And perhaps we'll come back and say more about that later, but he also has this a couple big theorems. A compact surface is orientable. Compact surface in R3 is orientable. Man. I would have thought the Mobius strip was compact, but obviously something wrong with my thinking. And a simply connected surface is orientable. So, all right, well, enough of that. I'm going to move on here. So now, I will let you guys choose your own adventure. So next up, we're going to talk about surfaces. We're moving on to chapter 5 here. And we're going to talk about surfaces. And the time will soon come, we're going to be talking about what's called the shape operator. And the shape operator, it turns out, is a linear mapping from the tangent space to the tangent space. All right? So we look at a surface, we can define this linear transformation from the tangent space to the tangent space, called the shape operator. I will prove this shortly. As we get further into it, we're going to discover that the concept of an eigenvector and an eigenvalue is important to the study of the shape operator. So my question to you, this is where you get to choose your adventure, is would you like for me to tell you about how to calculate eigenvectors and eigenvalues now or later? Now? Okay. I think that's a good choice. So let's talk about it. So let T be a transformation from Rn to Rn. Then V not equal to 0 is an eigenvector with eigenvalue lambda if T of V is equal to lambda V. And the eigenvalue is a real number here, okay? So this is definitions. So what I've defined at the moment is eigenvector. V is the eigenvector. Lambda is the eigenvalue. This is all done with respect to a linear transformation T. I guess I should have told you T is a linear transformation. Oops. All right. So, proposition, if beta, V1, V2, Vn, basis, well, I don't need all that. Well, yes, I do. If this is a basis for Rn, I just had visions of chapter 6 dance before my eyes, and I realized, oh, we do use non-standard bases in chapter 6 of O'Neill. If this is a basis for Rn, all right, and the matrix of T with respect to beta beta, what was it? Remember? So we do T of V1 in the beta coordinate system, T of V2 in the beta coordinate system, T of Vn in the beta coordinate system. So this is the matrix of T with respect to the beta basis that I introduced in a previous talk. All right, if that's a basis, and this is the matrix for linear transformation T, linear, with T of V equals to lambda V, right? Then what? Then the matrix of T with respect to the beta basis times the coordinate vector of the eigenvector is equal to lambda times the coordinate vector of the eigenvector. So kind of face the music here. In other words, if you were to call this, let's say this is called X, right? And if I call the matrix A, so I have A times X equals to lambda X again, right? And all I'm trying to get at here is we can also make the same definition for a square matrix. Square matrix, n by n real matrix, has eigenvalue lambda for eigenvector x if ax equals to lambda x, all right? So what I'm trying to say here is that if you have an eigenvector with an eigenvalue for a linear transformation, you have the same eigenvalue, right, for the underlying matrix of the transformation. So this means to study the eigenvectors and the eigenvalues of a linear map, we can either look at linear maps or we could look at the underlying matrix. We have a choice. All right. So often what's done is you just pick a basis and you find the eigenvalues and eigenvectors for the underlying matrix. And then from that, you extrapolate back what happened for the mapping. That's the approach. Okay? So I think what I'm going to do, since matrices are more, friendly, I'm going to focus the theory on the matrix case from now going forward here. But you should understand everything I'm saying about the matrix has a corresponding result for maps. All right, you can translate almost any theorem I'm about to say here for the matrix, the corresponding result about maps. So theorem A, so let A be n by n matrix over the reals again, all right? I can't write. Then A, there exists V not equal to 0 such that AV equals to lambda V if and only if A minus lambda times the identity matrix times V is equal to 0, which is true if and only if the determinant of A minus lambda I is equal to 0. Are we good? Hope we're okay. So the proof of this, I mean, let v not equal to 0 such that AV equals to lambda v, right? Well, that's true if and only if AV minus lambda v equals to 0, right? And you can rewrite that as AV minus lambda times the identity matrix times V equal to 0, right? And then you can factor the V out. Agree? So that's half the theorem, right? Let's say let v be not equal to 0, and lambda, I should also say lambda real number, such that, sorry about that, forgot to, anyway, who's question?
The eigenvector is a vector that when you apply a transformation to it, or it is a transformation?
When you apply the transformation to it, it is a vector. So yeah, fair enough, in here we've been using vectors as active objects, so take a walk down memory lane when vectors were static objects that we acted on for a second, yeah.
Okay, so it's a vector in that no matter what transformation you do to it, it only changes by a scalar multiple.
Now this is not for any transformation, it's for the specific transformation T, or now the multiplication by the specific given matrix A.
So T is only linear transformations. Is it any linear transformation?
It is a given specific linear transformation. Each linear transformation has its own set of eigenvalues and eigenvectors.
And then eigenvalue is the same as vector?
No, the eigenvalue is the number, the eigenvector is a vector. They're related, but they're different. Eigenvalue is a number, eigenvector is a vector.
The number is the lambda then?
The number is the lambda, right?
And the number applied to the vector gives you the eigenvector.
The matrix times the eigenvector gives us the same answer as the lambda scalar multiple of V. What this equation says is that when we multiply the matrix times an eigenvector, it just somehow rescales the vector. If lambda equals to 1, it would be a fixed point of the matrix multiplication, like AV equals to V again. But like generally speaking, it could be a multiple of V here. Now, so you guys good on this so far? Now I still need to explain this last step. Why is that true if and only if the determinant's 0? Let's look at that now. Well, so if A minus lambda I times V is equal to 0, for V not equal to 0, then the determinant of A minus lambda I has to be equal to 0. That's linear algebra, right? Remember, because is there more than one solution here?
Yeah. No. If the determinant equals 0?
Well, what I'm saying is, if the determinant was non-zero,
There would be multiple.
then the matrix A minus lambda I would be invertible. And then you can multiply by the inverse, and you could just get that V equals to 0 is the only solution.
Yeah.
But we're assuming here that V not equal to 0 is a solution, right? And the 0 solution is always there, right? Fine, but the point is you can't conclude that this does not imply V equals to 0 because we're assuming V is non-zero, which means that this matrix cannot be invertible. If it was invertible, only the 0 solution is possible for this equation, which then says that the determinant is not 0, which is to say that the determinant is 0. And conversely, if the determinant of a minus lambda I is equal to 0, then there exists v not equal to 0 such that a minus lambda I v equals to 0. That's also but this is something we discover in linear algebra as we're studying determinants. We learned that if the determinant's 0, then there is more than just the trivial solution to the homogeneous problem. And in this context, that means that we have an eigenvector. So all of this leads us to define, apparently this equation, determinant of a minus lambda I, is very special, right? So this, we make a definition, P of x equal to, or I'll use t, P of t equal to the determinant of a minus, and different folks use different conventions here. Like a lot of people might put, you could flip the sign here, I mean, maybe I should say, I'm going to leave it like it is, but some people will put ti minus a. You could go either way. You know what I'm saying? Like this theorem, I could have done lambda I minus a just the same, right? But anyway, this is the characteristic polynomial. I can't spell I spelled it right. Characteristic polynomial. All right, and P of t equals to 0 is the characteristic equation, right? Notice that we have immediately from the previous theorem and this definition that eigenvalues are zeros, solutions, if you will, of the characteristic equation. Questions? Yeah, it's all good. What, this characteristic polynomial, what's its order, by the way? Order 1? Nope. Here it has order n, generally speaking, order n. Because A is an n by n matrix, and if you think about what you're looking at the determinant of an n by n matrix that has t, right, appearing in the diagonal and then numbers off the diagonal. Think about multiplying that out. The leading term is going to be like t to the n times plus or minus 1. So it has order n. So the fundamental theorem of algebra tells us that given an n by n matrix, there are at most n eigenvalues, right? And they don't have to be n. Okay? Yeah. Now, if you take a complex perspective, right, and you look at a real matrix as a particular kind of complex matrix, and you allow eigenvalues to also be complex numbers, then you don't have to be so guarded. You can just say, well, there's always at most n complex eigenvalues for a matrix. That's true. And there's an interesting interplay between complex eigenvalues and real eigenvalues. But anyway, let's look at a couple of examples here before I get more into the theory. How about A is, 1, minus 1, 1, 1. What's the characteristic equation here? Well, the determinant of, 1 minus t minus 1, 1, 1 minus t. What's that? Yeah, ti here is ti is. Yeah, so it's that. So we've got t minus 1 squared plus 1. Now, set this equal to 0, no real solutions. In fact, here I get lambda equals to 1 plus or minus I. This actually has complex eigenvalues for what it's worth. So every matrix doesn't have to have any eigenvalues. It's possible that it doesn't, all right? However, what's that? Just to make an easy one here. Here. When the matrices come in blocks, if you've solved the subblock problem already, you can see things from what you already know. So like here, determinant of A minus lambda I3, that's the determinant of, 1 minus t minus 1, 1 minus t times the determinant of, fine, I'll write it out. Sorry, I'm using too much deeper magic. Let's see here, 1 minus t minus 1, 1 minus t, 0, 0, 0, 0, 3 minus t. So what I was arguing was when you have the determinant of a block matrix, it's the determinant of the blocks multiplied. So the determinant of the upper one by the upper block, we already know. It's that t minus 1 squared plus 1. And then times t3 minus t.
Okay, so here it says that these eigenvalues and vectors are the axis of which the linear transformation acts. And so,
Here? Where's here? You're Googling me?
yeah.
How dare you?
And so when we don't have real solutions, does that mean we don't have an axis on which the linear transformation acts upon, or is the linear transformation only acting upon a complex number system?
Well, if there are no, so for a 2 by 2 for a mapping on R2, what does it mean if there's no real, I can't prove this without like a 30-minute lecture, but in the 2 by 2 case, if you have a complex eigenvalue, what that means is that the transformation is a dilation and a rotation. And so with a dilation and rotation, unless the rotation happens to be by 180 degrees or 0, there's no vector which is fixed. They're not scaled back to where they started again, they're moved. This one happens to be a dilation by the square root of 2 and a rotation by 45 degrees. So that's what that is, like geometrically. But in 3 dimensions, if you have, in 3 dimensions though, if we have a linear transformation from R3 to R3, we cannot help but have an eigenvalue and have an eigenvector. It's, well, to quote Thanos, inevitable. So here the eigenvalue is 3. Why do I say that there has to be an eigenvalue for a 3 by 3 matrix? How do I know that? How can I state that with such, unqualified bombacity? What's that? Well, there has to always, well, it's not an axis though. This doesn't, it's not a rotation. It doesn't have to be a rotation. This is not a rotation. Something else. I reserve the term axis for, well, it depends what you mean by axis. If by axis you mean rotation, no.
And it says, which a linear transformation acts simply by stretching, compressing, and or flipping.
So you are looking at the singular value decomposition stuff. But anyway, the reason I know that is that if you have a 3 by 3 matrix and you look at the characteristic equation, what are we looking at? We're looking at a cubic equation in T. Is there always a real zero to a cubic equation? There is, right? The intermediate value theorem. If you take T sufficiently negative, if you take T sufficiently positive, it has to switch signs. So by the intermediate value theorem, there has to be someplace in the middle where it crosses zero. That place is the eigenvalue. There is at least one of them for a 3 by 3 matrix.
Does that go for all odd matrices?
Yeah, any odd side matrix must have at least one eigenvalue. Now, even matrices, no dice. Like you could have a 4 by 4 matrix. If you had a 4 by 4 matrix,
Does that figure like if it crosses at one point, it has to cross at another point, so you always have to have two?
if I did this, like a 4 by 4 matrix based on the, if I did this 4 by 4 matrix based on the A from problem 1, and I looked at the eigenvalues, I'm going to get an eigenvalue of 1 plus or minus I repeated. No real eigenvalues for my example 3. What are your question?
If you have, that means evens have to always have two, or like always have to come in pairs?
No. Other things can happen. Let's look at that. Evens don't have to come in pairs. Here's one. Let's look at this. Say 1, 2, 2, 1. This is a nice 2 by 2 matrix. All right. Let's find the eigenvalues of this guy. So we look at determinant of A minus, I'll use T again, Ti, or determinant of 1 minus T, 2, 2, 1 minus T. So what do we got? We've got T minus 1 squared minus 4. Do you like how I always flip the... It's just bookkeeping, you know, I just like to have the T first, but it's a squared, so it doesn't, you know, the minus gets eaten. 1 minus T squared is T minus 1 squared. So then that's difference of squares. That's T minus 3 times T plus 1, eh? That's just 2 squared. So I do T minus 1, T minus 1 minus 2, T minus 1 plus 2, difference of squares. So this gives me eigenvalues lambda 1 equals to minus 1, and lambda 2 equals to 3. What's that? That's it. That is a pair of solutions, yeah. But you said they have to come in a pair. Like, what kind of pair are we talking about?
No, you just have to have 2 points of intercept, not they have to be exactly the same.
Oh, well, I mean, they could be exactly the same too.
Yeah. Well,
But
is that 1 or is that 2? I'd argue it's 2 because they're exactly the same.
okay, well, okay. What are the eigenvectors, though?
-1 is A, 3 is A.
Yeah, we have to solve A plus I times, let's say, V1 equal to 0, and we have to solve A minus 3I times V2 equals to 0. So that's to solve 2 times V1 equal to 0, 0. Or it's to solve minus 2 minus 2 V2 equal to 0, 0. So I don't need to do algebra. I can guess the solution to these. Can you tell me V1 equal to what?
0, 0.
That is the one choice we cannot make.
Oh yeah, we can't. -2.
I mean, you're right that 0, 0 was a solution. Totally right. But that would not be an eigenvector, which is what we're looking for.
So something that multiplies that.
I'll do this one. 1 minus 1.
Oh, you have to add. The other one is just ones.
Now, to be a good citizen of the mathematical world, divide by the square root of 2. Divide by the square root of 2. Because then we have the basis beta, 1 over root 2, 1 minus 1, 1 over root 2, 1, 1. This is what's called a orthonormal eigenbasis for A. So some really cool stuff. If we have t of x equals to ax, right? Continuing number 4. Suppose we have a linear transformation t such that A is the matrix of t, right? What does the matrix of t look like in the beta basis? Right? So t of v1 equals to what? AV1, right? AV1 was what? Minus V1. T of V2, what is it? Nope. Remember, we designed it so that A times V2 is 3V2. So what is the coordinate vector of this with respect to the beta basis? What's the coordinate vector of this with respect to the beta basis? T of V1. Let me rewrite it. What's the coordinate vector of that? What's the coordinate vector of this? Remember, the coordinate map converts the abstract basis to the standard basis, was what we learned.
Oh, it was the,
So E minus E1, right?
yeah.
Which is explicitly minus 1, 0. This one, 0, 3. So put this all together. What's the matrix of T with respect to the beta basis?
3 over root 0.
Yeah.
-1.
Uh-huh.
-1 over root 2.
No, there's no root 2s here. It's just the eigenvalue.
Okay, and then 0, 3.
Yep. So that may start to answer the question, why are we looking at eigenvalues? Well, partly because eigenvalues allow us to diagonalize a linear transformation if it's possible. If you rewrite the formula for a linear transformation in terms of an eigenbasis, the matrix of the linear transformation will be diagonal. And that's a beautiful thing. This is an even more beautiful thing because this is an orthonormal eigenbasis, which means that if you look at the matrix of beta, the inverse of that matrix is the transpose of that matrix, right? And in fact, as a calculational nicety, this is nothing more than the transpose times A times beta again. If you do this similarity transformation, actually, because beta transpose is beta inverse, that is a similarity transformation of the matrix A to a diagonal matrix. So this example is very nice. Right? Now, you might ask the question, so, okay, this is nice that this happened, but it doesn't always happen, does it? Right? We saw in example 1, there's no eigenvalues. If there's no eigenvalues, you can't very well diagonalize it like that, can you?